It's kind of bad when, people are embarrassed to introduce me. Okay. So, I got to start off by saying that this is a work in progress. I think there is something really deep and fundamental in here, and yet I can't quite put my finger on it. So giving the talk is actually a way of helping me try to clarify my thinking. So I appreciate you all being guinea pigs, and I would really appreciate feedback on it. Okay, you're supposed to applaud at the end of the talk, and I go, oh, right. No, this actually is a thank you to the people here, because I owe an awful lot of the pleasure in my life to the work that people, at this conference have done. The Erlang core, a whole bunch of people working on, say, nerves, which is my current joy. And even Larry Wall has given me, I said to him a couple of nights ago, a fantastic amount of pleasure, and has also changed the future of computing for us all. So I want to say thank you, and I want to think about just the people I talked about, right? These are people that have changed history, and, we're all kind of like old, kind of gray-beardy kind of people. But you know what? These people kind of know what they're talking about. And what tends to happen over time is these old people get new people come along. You might want to think about this as Erlang and Elixir. And the problem for the Erlang folks is Elixir currently has the ring. So what I want to do actually is to go back and look and honor some of that experience, because us Elixir folks, we tend to go around saying, hey, we got a really cool language, right? And ignore a whole bunch of the really important stuff that we knew in the past. And I think this new stuff actually comes forward and applies to what we should be doing tomorrow. Just to prove that I am also one of those old farts, here is a picture from, I think, 71 or 72 of me and my friend Toby Bailey. The caption says, programming an analog computer. Actually, it was turned off at the time. We were just looking like we were programming. So, let's talk about some old stuff. Right? This is all going to lead up to these ideas I've got about how we should program today, but I just want to get some history and some background into it. So state machines. We all know what a state machine is. Right? It's a way of parsing a stream of events. We start with an initial state, an event comes along, and depending on that state that we're in, that event makes us go to a different state, potentially. And that just repeats over and over and over again until we're done. A classic example is like one of these push-button locks. So let's imagine that the code for this lock was 131. This would be one of those cool, I hate programming challenges for job interviews. I don't think anyone should ever do them. I've never done one. But this is actually a cool one to set as a programming challenge, because my guess is about 80% of the people would actually get it wrong. Because you can actually unlock it, obviously, by giving it 131. You can also unlock it by giving it 817 and 131. And you can unlock it by giving it 3131. The trick one, though, is that one. Because if you're just looking for a 1 followed by a 3 followed by a 1, then you're going to bolt out on the second 1, go back, and it's just not going to work. Most people get that wrong. But doing this with a state machine is really easy. Except it's not. Okay, first of all, I apologize. This is Ruby code, but who cares? This is how many people would code a state machine. So what it is basically we have an instance variable here, state, and then we have a function that accepts the next event. And depending on what state we're in, we look at the event and say, in that case, I want to go to the next state and change my current state. And we just do that for each of the possible states. It's code like this that makes people think they need to go out and find a library to do state machines. Right? I have no idea why people do that. As you'll see in a minute, you don't actually need it. But this is what people code. I prefer to do it like this. A state machine is simply a hash, an associative array, a dictionary. And in this case, I'm using the state. Whoa. I'm using the state as the key is the state. And then for each state, I have another hash which says if I get a 1, then transition to that state. If I get a 1 here, transition to that state. Yeah? And my entire event handler thing is I just basically go from the transitions to the current state indexed by the key, and if it doesn't match, then I'm just going to go back to my default state. So that's kind of easier. So let's take it a step further. Let's add in some external real-world stuff, because one thing state machines don't talk about is actually interacting with the real world. So let's make it do that. Here I have added what some people might call a model, right? The outside world. And in this case, it's controlling the light on the lock. And all you do is you pass it a color, it turns the light on. So I've augmented my little state machine language here to add the ability to put not just the next state, but also the next state and a function to invoke as I transition to that state. And it's really pretty lightweight. The only thing that happens is if I'm in the last waiting for a 1 and I get the 1, now I am unlocked and I will set the LED to green. Otherwise, my default transition, which basically means I've always gone back to the start state, is set the LED back to red. And by doing that, it'll always go red if you get it wrong. So let's take that one step further. Same code, but split up a bit more. So now I have my model, which is the thing that my state machine is manipulating. I have my set of rules, which is what the state machine actually does. Then I have a generic finite state machine. It knows nothing about locks and LEDs or anything. All it knows is you pass it a set of rules and it does the business. So what actually is a transition? Well, at its simplest, a transition is just an input and a state that produces a new state. And along the way, it's going to execute an action, potentially. You might ask yourself, what is a program? Exactly the same thing. If you went to, like, Computer Science 101, at some point a professor had sat there and drew the picture on a board, right? Input, arrow, processor, output, or something like that. And that's what we're looking at here. So a state machine is really a whole bunch of little small nested programs. This is where we're actually getting to in the end. It's, pretty straightforward. Online order processing, you can see how that works. In this case, our state is the session, if we're talking to Twitter or something. So my assertion is that a program is a deeply nested set of individual transitions, and each one takes an input and a state and produces a new state and possibly an updated input. And you'll see why I say that in a minute. So this is the only diagram you need to program, right? If you're one of those people that loves doing, UML and class diagrams and all that kind of stuff, right? Well, here's your new nirvana, right? And that's all it is. And the cool thing about it is you'll notice the output and the input are the same, so you can chain them as much as you want. They compose. Isn't that wonderful? So you can look at something like this. This is a deliberately ugly example just to show it can be done, right? So here we're calculating something to do with an order. We're sort of terminating or finalizing an order. So we're having to go through it and do all sorts of things to it. And you'll see what we're doing is we're gradually going through and we are taking the inputs and using it to produce sequences of outputs. Now here's the thing that's really important. This looks like I'm describing the flow through a program. But I'm not. There is nothing about time in that flow. All I am doing is saying that if I have this as my current state, then I can execute that. If I don't yet have this, then I've got to hang around for a little bit. So even though this shows you the dependencies of state, in reality, each of these could be a totally isolated, free-running process that's just waiting for the correct set of inputs to come along for it to be able to do its thing. There is no time element in this kind of programming. And that's the key. Because one of the things that we try to do when we're coding, well, Thomas's rule of good design, right, is a good design is easier to change than a bad design, right? As far as I'm concerned, that's the only rule of program design. And one of the ways we make our designs better is by reducing coupling. And one of the things that we do with functional programming is we have a really major bit of decoupling in that we decouple our state from our functions. And although that's kind of scary if you come from an OO background, it turns out to be remarkably liberating, and I think that's one of the main reasons that functional programs are easier to change. But we still have coupling in our functional programs. And the coupling is this kind of insidious temporal thing, that I'm going to do this, then that, then the other. Now, outside a particular process, obviously we don't have that on the beam. But inside each chunk of code, inside each function, we still say A, then B, then C, then D. And that is coupling that we don't need. So, how do we code this? Well, too many people hand code it. We could code it as a state machine. I think we have the opportunity to do something better, though. I think we can code these transitions using pattern matching. Right, I always used to use Fibonacci numbers as my examples of pattern matching, and then some mathematician said, oh, Lucas numbers are way cooler, right? And the only difference is that rather than having 1, 1, it's 1, 3, right? So this is pattern matching, calculating the Lucas numbers. And, okay, everybody's seen this, everybody knows this code, we all do this kind of stuff, right? The cool thing here, obviously, is we have no conditional code, nor do we have any sequencing that says you have to do this, then this, then this. It just happens that way, because things only trigger when their preconditions are met. Here's our lock expressed using pattern matching. So we have a group of functions here, none of which has a variable parameter. They're all fixed parameters. But it's exactly the same thing. And the nice thing about this is, because they're all functions, I can return the next state, but along the way, I can also have side effects like setting the light to green. I code a lot like that in my everyday coding, right? And it was kind of looking at code like that that led me to think about some other things. And it also came about because increasingly over the last couple of years, I don't know about you, but this word reduce and reducers and stuff has become like, you know, the new object orientation or something. It's a really big buzzword, right? Everyone's talking about reductions and reducers, and you can't have a JavaScript framework nowadays unless you've got reducers in it, right? So a reducer is that, right? It's a function that takes an input and a state and produces a new state. That's all a reducer is. Why is it called a reducer? Because it is the function, it's the signature of the function that you pass to reduce. And it was going to be called a foldeller, but no one could pronounce foldeller, so they called it reducer instead. So in this chunk of code, which is our lock FSM, here is our entire state machine. Right? This is why you don't have to go and buy a library to do state machines. It's called reduce. Right? In num.reduce, initial state is you initialize the lock, and then we just feed it through lock.accept until it finishes. Nothing else to do. And there are our reducers. They take an input and a current state and produce a new state. So our reducers implement a transition that look like that, and I'm about to extend them to look like that. So why should we code with reducers? Well, firstly, it tends to lead to incredibly small, little self-contained functions. Functions that are really easy to understand. It gets rid of this shared state between lines of code, right? My personal view is a variable is a smell. And if you can get rid of your variables, then you've actually improved your code. I find it a lot easier to read. It's incredibly easier to test, because all you're doing is testing one-line functions by feeding a particular state and an input and making sure you get a particular output. So easy, in fact, that I don't bother to test them anymore. And they are easier to reuse. So, okay, say hello to Dobbin. Dobbin is a horse that we're about to beat to death. So, the sum of an empty list is 0, right? Here's our reducer. It doesn't actually have any input. Otherwise, the sum is ahead of the list, blah, blah, blah. You all know this. So here we have list summing written using exactly that pattern, right? It all just works. And the pattern matching is going to do the state transitions to get us to the end where we finish, and it's all wonderful. Why am I showing this? Well, I'm showing this because when you explain this in a book or something, you end up showing a bit of code that looks something like this. Yeah, you're trying to examine how it works or explain how it works. So you kind of expand it out like this. So you could write our code using the new universal programming notation as simply as this. You have an input and the state becomes the empty input and the new value. Okay, so here's where the horse beating comes in. I didn't draw it. It's not me. I didn't draw it. Okay, so I now know how to please you guys. I'm going to go more dead animals. All right. Okay, so there's something really obvious but interesting about this. Here is our state, and in general terms, here is our time. First thing to notice is it doesn't have to be in that order. It can be in any order you want, but it happens to execute in that order. But the really cool thing is, if you add up the input and add it to the output, you always get the same number, 16. Well, duh, of course you do. But that idea leads us to the idea of invariants. Now, if you are old and gray like me, then when you went to college, you learned about program proving, back before they decided they couldn't actually do it. And you learned about how to program using invariants. An invariant was basically a statement of what is true at this particular point. Right? You say, this is regardless of the values in the state, this relationship holds between them. And if you can use that, and a whole lot of time, you can actually prove that an if statement sometimes does what you want it to do, right? Totally waste of time long term. However, thinking about invariants leads to really nice bits of design. Because the more you can think about an invariant, the tighter you can make your loops, the easier you can know it's going to work or not work, whatever. So my point is that a correctly implemented reducer is going to transform state while maintaining the invariant. Right? That's obviously the case with sum. But I think what we're looking at here is a wider picture. So this is my most portentous slide ever. The most important thing in programming. Truth is conserved. All right. I'm sorry, they're not dead. Actually, they are. They're stuffed. Well, you couldn't get all three to sit in the same place like that otherwise, could you? That took me forever. All right. So, the law of conservation of truth. Unless your name is Kellyanne, truth is neither created nor destroyed. It merely changes its representation. Yeah? You're never, ever going to be able to change truth. That's kind of the definition of it. Yeah? But you can certainly change the way you represent it. And that is all that programming is. All of programming, nothing apart from maintaining truth from beginning to end. So sum conserves that truth. It transforms our state, but it conserves the truth. All right. Okay, you say, big deal. Anyone can write a sum. Why do we care? And we care for the same reason we care about any programming practice. And that is, a good programming practice informs you. It doesn't just let you get away with something. It actually tells you, this is good, this is bad. It helps you write better code for any definition of better you want, apart from probably Joe's, who would say it's not quality. But it's got to be, this idea leads to some really interesting code. And so I started playing around with this and produced a framework called Diet, which is not a framework, sorry. I produced a really crappy little library called Diet that I enjoy playing with. It doesn't stand for anything unless you want it to, but it's called Diet because it's all about reductions. So come back to our sum of a list. I promise, I think this is the last time I sum a list. Hey, can you give me a quick time check too? Or how much is plenty? I will carry on while he's checking. So here's our set of truths, if you like, for summing a list. We know that we have, in our whole universe here, we have a list and we have a result. We know that at all times the sum of the elements in the list plus the result is a constant. Oh, of course it. And we know that we finish when the list is empty. Okay? Now I've shown you that in code. Let me show it to you in Diet. So Diet is simply some macros in Elixir that let you express that in kind of like a more compact form. So in my module, I use Diet transformations, which is what these guys are, and I have a series of reductions. So here I'm saying, okay, so I'm tending to use the first element of a tuple as like a verb, but that's just, it stops you getting into some ugly kind of like circular things. So here I'm saying to sum a list, well, the fact was we have to have a list and a result. And here we don't have a result. All we have is the list. So the first thing we have to do is to add our result in, right? So we're going to sum into our list. What value does the result have? Well, we know that the sum of the list plus the result has to be the same as the sum of the list, so it has to be 0. No choice. Next, the sum of the elements of the list plus the result is constant. So here I'm going to sum into a list that has a head and tail into the result, and I do the obvious thing. And then finally, if I'm going into an empty list, then there's my result. Again, not dramatically new. So how does this actually execute? Well, I have a thing called diet.stepper, and you pass it one of those descriptions. So in this case, it was in the module list sum. So I pass that module in, and I pass in an initial state, which in this case I don't care about. And then I just run my stepper, and I pass it the initial event. So the initial event in this case is sum 1, 2, 3. And how does that then work? Well, the stepper basically looks at this as a big pool of challenges. And it goes into this pool and says, okay, which one can I match? And the first one it matches, it's going to execute. So in this case, it's going to match the sum list, and it's going to produce a new fact, which is sum into list 0. It hasn't finished yet, because now it's going to take that new one and go back into this list and look for another one that matches, or look for any one that matches. So in that case, this one doesn't match, this one does, so it's going to apply this one. We're going to sum into, we're going to do something new, et cetera, et cetera. Eventually, it's going to get to this guy down here. Sum into the empty list with the result returns the result. But now, the result doesn't match anything. So the stepper goes, not my problem, and passes it back to you. And that's why, when you run that, you get the result come back out again. Let's make that slightly more, oh, actually, you know what, let's do it. All right, live code time. Okay, so with any luck at all, I actually have stepper aliased here. Yeah, all right. So I'm going to produce a new stepper. And I can't remember what I called it. ListSum? It was example.listsum. And no state. Okay, ignore that. That's just implementation. Right? So now I'm going to produce the result and the state, a new state, by running stepper.run on that stepper, and I'm going to pass it some, oh, let's be different, 3, 2, 1. All right? And honestly, I don't care about the state at the end of this. All I care about is the result, so I'm just going to put the R there so it just displays the result. And I got something, oh. Yay, there's my result, okay? But, no, wait, all right? I'm English, so I'm bound by contract to say, but wait, there's more, all right? Because this stepper is not just executing code. If I was to say diet.debug and ask it to debug that particular stepper, it'll say, okay, I'm now looking at example.listsum. And one of the interesting things I can do is say, hey, show me a trace of what actually happened. And here it's showing me the set of things that it actually went through to produce that result. Yeah? And if I wanted to, I could dig into any one of those, and it shows me, the details of what actually happened. I can also, well, let me show you that later on. Okay, so let me take another example. Let me get out of there. Slightly more complicated example. This one I use all the time just because it's just that bit more complicated than summing. And that is, you're given a list of things, and you want to run length encode it. So if you have a run of the same values in the input list, you want to replace it with the value and a count in a tuple. And the reason I like this is it's another one of those programming challenges where you give it to people, and typically they'll get it wrong first time. They get most of it right, but there's always boundary conditions that throw people off. The most common one that confuses people is what happens if the run ends at the end of the list. And they have to handle that as a special case or something, if you're writing lots of ifs and loops and this kind of stuff. So instead, let's just ask what is true. Well, just like everything else, we're going to change our input into our output. And we know that if we were to take our input as it currently stands and our output as it currently stands and concatenate them, it will always be the same. Yeah? And then when the input becomes empty, the output will be the run length encoded list. And there's a few other things we know. We know that if our list starts with a duplicated value, we're going to replace it with that value and a 2. And if our list, this is the wrong way around, I've just noticed. If our list started with one of those duplication things and then has an A after it, we're going to bump the count and move on to the next one. So here is our run length encoding, written using that reduction style. So the same thing we have to do in the previous one, we have to create ourselves the output. We're not past it. So we're going to say RLE of a list is RLE of a list plus an empty list. Ignore that one. Here we have the case where the first 2 elements of the list are the same. So what we're going to do is we're going to replace those first 2 elements with the A and a 2. If we have one of those tuples followed by the same value, A, then we just bump the count. Otherwise, we copy the input to the output. And the cool thing about this is, you remember I talked about if you write like this, it's so easy to reason about the code? We guarantee that this thing is going to terminate. Because on every single match, we're removing something from the input. We have no choice but to terminate. And it works.
Does the order of those things matter?
It does them top to bottom, just like Erlang and Elixir do. And yes, it does.
Sorry, I didn't quite get that.
Yeah, so the order of execution does not matter. The order in which it matches does. if that makes sense. Right? So it doesn't actually execute each one of these things in turn, and we're not giving it a sequence to execute in, but we're also saying this has a higher priority than that. So, again, we can do oh, I don't have RLE, that's why. Is it example.rle? Yes. Okay, and then I can do r comma s equals stepper.run s, and I'll give it some input 1, 2, 2, 2, 3, 4, 4, 5, 5, 5, 6, 7, 8. Why not? Okay, and then I'm just interested in the result. Oh, interesting. I didn't give it the command RLE. I just passed it the list. So it went, sure, I don't recognize that, have it back. Okay? So I'm going to put RLE in front of it. This is a feature, not a bug. I thought it was a bug, but last time I actually gave this a very different variation of this talk in Chicago 2 nights ago, and someone said, oh, that's really cool, because that way you can code, and when you miss things, it will report it back to you. I think, yeah, exactly right. All right, what am I doing wrong? Oh, it's in code. In code. Sorry about that. I knew it was going too well. Yeah, nil desperandum. All right. So, and again, though, right, this is a more complex example. So let's use our debugger again. And let's have a look at the trace this time. Whoa. All right. Let's shrink that down a bit and do it again. And that didn't help. All right. Sorry about that. Take my word for it. It's a lot of stuff. But this shows you every single step it took along the way, which means that if you have an error, if you have a bug, which of course you're not going to have with this kind of way of doing things, but if you did have a bug, it's going to be very easy to see why you didn't pick up that extra 2 or whatever it might be, because you can just see it in each one of the transitions. So let's really push the boat out. These are all kind of like vaguely academic things, but let's look for the real world, right? And what's more important in the real world than a game of Hangman? So let's write a stepper version of the game of Hangman. Let me see if I may actually have this on the slides. Yes. So this is the game of Hangman expressed as a set of reductions. Like the door lock, it actually uses an external state. And in this case, the state is the module that holds things like, or it's not a module, the structure that holds things like the current word to guess, the number of guesses that you've taken, all that kind of stuff, right? It's all stored in our state. And in our reductions, the state is such an important thing that I just make it available for free. So here I call model name game. And that means in all of our reductions, I can use game, and that's just going to refer to the model. And the model, I'm at the top here, I tell Diet that I'm using Hangman model as my model, and I'm going to call it HM because I can't type Hangman model all the time. And otherwise, then it just runs through here. And again, the order it actually executes in, the order it matches in is top to bottom, but the order it executes in, who knows? But you start off by to make a move. First thing it does is ask the model have I already used this letter, right? If I have already used this letter, it's going to just respond already tried. Otherwise, it's going to set our new state to record move and pass in the move. And record move is going to go, oh, I need to update the model. So it explicitly says update the model. And I do that. Jose hates that. I do this because I think it's important to show people when you're updating the model and when you're not. Because you look at this, there's only 2 things that update the model in all of this, right? And that's a big thing. So you don't want to read the whole thing, and it'll be on the slides when I get around to publishing them. But the idea is that this actually will execute a game of Hangman. And it's really cool. So let's actually go try and run that. Hangman. Okay, now if you want to keep the suspense, avert your eyes while I type the word we're going to guess. I do have a version that uses the dictionary, and I just hate losing in front of a crowd of people. So, all right. So there's our word. So let's start running it. R, S equals stepper.run s, comma, what did I call it? Make move. And I'm not cheating, let's just start with an A. Yeah? And again, I don't care about the new state, I just want to look at the result. Hey, it was a good guess. Right? Not exactly the best user interface, but we can build on that. So let's try something else. Let's go A, B. All right, there's a strategy. You start at A and you go to the end. Yay, good guess. Clearly, it's the best strategy we can use. So let's keep going while we're on a roll here. Let's try C. Damn. All right, we have a bad guess. And I don't like that, right? Because I really want to be perfect. I mean, who doesn't? So let's just go back into our debugger here. .debug s. All right. And here is the list of states that we went through to get to what happened. The numbering system here is n.n. This means this is the first time I called it. And then inside that, it actually ran 8 separate transitions. And then here, it ran 8 again, and here it ran 8 again. Okay? So, and you can see that at the end of my transition here, 1.8, I got a good guess. Yay! You'll also notice that this little dot changes to an arrow on some of them. That indicates that the state's changed on those particular ones. So if I get a bug that's something to do with a state change, I could do something like, let's have a look at 2.3, and it shows me that what happened was I've added a B to the list of guessed things. You know, sort of highlights the changes that it makes as it goes along. Now, I've got this problem that I made a mistake, and I don't like making mistakes. So, you know what I can do? I can clone my history up to a certain point. So let me clone my history. Let me just remember, I think it's clone, up to 2.8. All right. You'll notice now that it's changed from Hangman 0 to Hangman 1. That means that I'm on my second copy of Hangman, my clone, right? And now I can start making moves. If I could remember how you do that. Hang on a second. R, that's right. So let's R, make move. So I had, what did I have? I had A, B, let's do M. Good guess. Let's have a look at our history now. Ha! I now have just 3 states, and it went straight from B to M. I'm perfect. Right? And we can finish that off. So R, oh, actually, just do that. O, T, W, game 1. All right. This is actually really pretty cool. The fact that I can go back and both inspect history, but also fork it and then move forward is great. Imagine, for example, you have a server where the state is kind of expensive to set up. Then what you could do is run through that state setup once and then fork. And now you've got, everybody else shares that initial setup. Yeah? If you need auditability, no problem. And there's obvious implementation issues, like potentially this is an infinitely long list, and you know, small details like that, but that's tractable. You know, there are many ways of compressing this down. First thing I can do is replace each of the individual substeps with a compressed version once it gets to a certain size, and then I can do more and more and more compression, and I can get it down pretty tight, except the fact that the further back you go in history, the more granular it becomes. So, my point is that programming is transformations. And that's what we need to think about. Nested, composable transformations. And the rule for programming is, number one, work out what should be true. Number two, make it true. And we call that establishing the initial conditions. If you're a Rails programmer, you call it validates presence of, or something like that, right? It's what you do to get your data into a state where you can trust it. And then your only job is to keep it true as you make lots of transformations. And if you do that, your programs will be correct. So, this is the slide I would use if this was a PhD presentation. Programming is reducing input to output in the presence of state. Yeah? This is the slide I would use if I was Jane Austen. Programming is truth. But the slide I would use if I am me is programming should be fun. Thank you.
We have one question.
Oh, God.
Couple of comments. To start with, your examples of some of the things are just Erlang programs. If you take the colon out, put a bracket, move it to the left.
Of course it is. Of course it is.
But you're interpreting them
Exactly.
instead of compiling them.
Yes.
Why?
Because Erlang can't do me the history thing that I can do like that.
The debugger.
Yeah, not in, no.
That's a stack trace in the debugger.
The point I'm trying to make is, and when I showed the grade,
They're the same. Well, I mean, you're reinventing that.
no, I am, that's why I showed, you're Gandalf. Haven't you worked that out yet? You're Gandalf. Right? And yeah, right, yeah. Was it 2 years? The thing I'm trying to get to here is that all of this stuff, none of this stuff is new, right? I mean, the Elm folk like to think, oh, we invented reductions and stuff. No, they didn't. I mean, that was 1958 probably, or something stupid like that. Right? No, none of this is new. And when I said that what I'm doing is honoring the past, what I'm saying is I'm going back to the things that, yes, Erlang can do and Prolog could do before it. Yeah? But what I'm trying to do is to put it into a context where now we can look at this in a bigger picture and start using it as a tool, right? So it's not just a question of saying, yeah, Erlang could do this. Erlang could do all of this, any of this. Assembler could do any of this and all of this, right? It's really just a question of how you think about it, right? How does the language encourage you to think about things? And what I'm thinking is, or what I believe is, that if I make it easier to think about things in terms of reducers, people are more likely to use them. And if that's how they do things, then I think the quality of programming will increase. So I'm not in any way saying that this is brand new.
And the other comment was, of course, in Erlang, every single equals in the program, every single equals is a statement of true equals true, because if the equals fails, it crashes, which is why my little motto, let it crash, is actually a statement that every statement should be true.
Absolutely.
And so you don't need any unit test or anything like that, because it unit tests every time you have an equals.
No, you're doing a test every time you have an equals that has a fixed value on both sides.
Oh, yeah, well, okay. It's a free variable.
I love you anyway, Joe. Anybody else? No, because Joe and I could go on all night like this. It's okay.
Who's our next speaker, so we can go on.
Oh, God.
Okay, one more question.
So not really a question, more of a challenge for you. I'd like to see a JavaScript VM written in this, right? So actually being able to take JavaScript in and do things with it.
Can I ask why particularly?
Why not?
So are you saying you want to see a JavaScript interpreter written using this style, or do you want to see this style written in JavaScript?
I want so I'd like to see if you can actually do this, right? And like feed it like JavaScript instructions, and it actually doing what it's supposed to be doing.
I don't see why I couldn't, apart from the fact that I'm probably likely to die before I'd finish, or kill myself, one of the two. But actually, it does lend itself very well to that form of problem, because when you think about it, parse transforms are fundamentally what we're doing, right? So we're parsing, we're matching a pattern, and then we're doing something with that pattern. So you could actually see many of that kind of problem solved. Interestingly, I wrote a markdown parser. It's kind of like, I started off as a pet project because it's like one of my challenges when I learn a new language, just to write a markdown parser in it. And I wrote it in Elixir, and it was one of the first large Elixir programs I wrote. And it's not written using that notation because I didn't have it, but it's actually written using pretty much that style. So everything is done as a match followed by a new state. And it works a treat. I mean, it really does work well. But JavaScript, maybe, can I leave that as an exercise to the reader?
Thank you.
Thank you.
Thank you very much.